Hello, welcome to Introduction to Composites. Today is the last day of this ongoing week, which is the 9th week of this course. We have been discussing the formulation stress strain constitutive relationships for different types of materials, and we started with anisotropic materials when we found that it has 21 independent elastic constants. Especially orthotropic material in 3D has 9. Material which is transversely isotropic, that is its properties in a particular plane are isotropic. Such material has 5 elastic constants, and today we will discuss another category of material which is known as especially orthotropic in plane stress. In plane stress. So, it is not just especially orthotropic, but it is in plane in a state of plane stress. What is the characteristic of the material? First thing is that it is thin. It is a thin material. Second is it is in a state of plane stress, and so suppose this is the material, and because it is thin, this dimension is not large. Suppose this is my loading direction 1 and this is 2, it is especially orthotropic. So, this is because it is especially orthotropic, let us say fibers are aligned with the one axis. Okay. So, one axis is same as the material axis L, and this is same as that axis T. So, it is especially orthotropic. So, fibers are aligned with one direction, it is thin, and it is in plane stress. And what is the meaning of plane stress? That the stress in 3 direction, in the thickness direction, stresses in thickness direction are 0, which means sigma 33 is equal to sigma tau 13 is equal to tau 23, they are all 0. Why is this kind of a material important? The reason we are considering this material is that a lot of times when we fabricate composites, we make them using individual layers. Okay. We make them using individual layers, and these composite layers are very thin, and typically the stress in the z direction for them is very less or 0. Okay. So, to understand the behavior of such materials, and we stack them up, and then from each we take several such layers, and ultimately we have a laminate. So, to understand the response of every single layer, we have to understand how does a especially orthotropic material behave when it is in a state of plane stress. That is why we are trying to understand them. So, let us see how many elastic constants such a material has. So, what do? We develop the stress strain relations for those. So, we know that for especially orthotropic material, which is not in, which may or may not be in plane stress, it has 9 constants, right? It has 9 constants. So, first we do that and then we simplify it. So, sigma 11 is equal to C11 epsilon 11 plus C12 epsilon 22 12 plus C13 epsilon 13. C14, 15, 16 they are not there because the material is especially orthotropic, it has only 9 constants. Okay. sigma 2 2 equals C 1 2 epsilon 1 plus, actually I have made a mistake in terms of notations, because now we are no longer using tensor notation. So, sigma 1 is equal to this epsilon 2 epsilon 3, no shear strains. Sigma 2 is equal to C 1 2 epsilon 1 plus C 2 2 epsilon 2 plus C 2 3 epsilon 3, and sigma 3 is, in our case it is 0, right, but if it whether it was 0 or not, the expression for this will be C 1 3 epsilon 1 plus C 2 3 epsilon 2 plus C 3 3 epsilon 3, and this is 0 for plane stress. Okay. This is 0 for the plane stress situation. So, we can say, so let us say this is equation A, B and C. So, from C we can calculate epsilon 3, we can calculate epsilon 3, epsilon 3 comes out as minus C 1 3 epsilon 1 by C 3 3 minus C 2 3 epsilon 2 by C 3 3. Okay. So, this is equation D, and we put D in A and B, we put equation D and A and B. So, remember how many equations are there? There should be 6 equations. Right now we have written only equations for sigma 1, sigma 2, sigma 3. There are 3 more equations for shear stresses, tau 1 2, tau 2 3, tau 3 1. We will talk about those later, but right now we are just considering the equations for extensional stresses. Okay. So, if we put D in A and B, what we get is sigma 1 equals C 1 1 minus C 1 3 square by C 2 3 epsilon 1 plus C 1 2 minus C 1 3 C 2 3 by epsilon C 3 3, yeah, epsilon 2 and C 2 equals C 1 2 minus C 2 3 C 1 3 by C 3 3 epsilon 1 plus C 2 2 minus C 2 3 square by C 3 3 epsilon 2. Okay. We call this term as Q1, we call, or Q1 1, we call this term as Q1 2, this is again Q1 2, and this term is called Q2 2. So, we have developed expressions for sigma 1 and sigma 2 in terms of epsilon 1 and epsilon 2 for the plane stress state, because we have imposed the condition of epsilon 3 sigma 3 being 0. Okay. Next, look at shear stresses. So, for shear it is pretty simple, sigma 2 3 sigma 2 3 sorry, this is a shear. So, I will use the term tau, tau 23 equals 0, and tau 23 is what? Is equal to C22 minus C33 divided by 2 times gamma 23. Okay. Now, what this means is, if this left side is 0, then there should not be any shear strain. So, which that means is gamma 23 is 0, not that C22 minus C33 by 2 is 0, that can be anything. But if I am not applying shear strain in the 2-3 plane, then it will not generate any shear strain. So, gamma 23 is 0. Similarly, tau 13 is equal to 0, tau 13 is 0, and that implies gamma 13 equals 0. And lastly, tau 12 is equal to C66 gamma 12. Okay. In general, the full scale special orthotropic material we have shown. See, these were the equations for full scale specially orthotropic material. It had 9 constants, 6 equations, but because of plane stress condition, these terms do not exist. So, 3 equations go away, right, and we are left with 3 equations only. So, the equations for special orthotropic material in plane stress what are those equations? We have only 3 equations, sigma 1, sigma 2 and tau 12. Okay. And what are the 3 strains? Epsilon 1, epsilon 2 and gamma 12. Okay. And the elastic constants are Q11, Q12 0, Q12, Q22 0 and Q66, where, oh, so I forgot, this term C66 we call Q66. So, we have 3 elastic constants Q11, Q22, Q12 and the 4th elastic constant is Q66. So, these are the relations for especially orthotropic materials. Okay. And then finally, for isotropy, we have 2 constants, and we will not discuss this because we are short on time and the focus of this course is on orthotropic materials. So, we will not talk about it, but in general E and mu are considered as 2 independent constants. All other constants, shear modulus, bulk modulus can be expressed on terms of E and mu. So, let us have a quick summary. Anisotropic materials, 3D materials we are talking about, 21 constants. Then we have special orthotropy, again in 3D, not in 2D, we have 9 constants. Then we have in plane isotropy. So, the material can still be thick, can still be thick. So, it is a 3D material. We have 4 constants. And then we have special orthotropy, plus plane stress. What that means is that material is thin. So, this is a 2-dimensional material, it is very thin. 4 constants, and no, I think this one I made a mistake. This is 5 in plane isotropy. Transverse isotropy, that is a more precise word, transverse isotropy. So, this is the overall picture, and what we will do tomorrow, next week, is we will continue this discussion. Maybe in the first lecture we will close this discussion on different type of materials in 1 or 2 lectures, and then we will start developing a theory for figuring out how do laminates made up of either transversely isotropic materials or especially orthotropic materials which are in plane stress, how do they behave when we attach several layers of them on top of each other, then how the overall plate behaves, the overall composite laminate behaves. So, that concludes our discussion for today. We will meet once again next week. Till then, have a great day and a nice weekend. Bye.